Good afternoon, everybody. The talk from my title today is Observation of Black Carbon, Ozone, and Carbon Monoxide in the Kali Gandaki Valley in Nepal. The impact of anthropogenic emission on climate is becoming more evident. Emission rates downwind of the Himalayas has increased in the past decades, and the alarming rate of glacial melting and the incessant number of population that are being exposed to extreme levels of pollution in South Asia has grasped both national and international attention. This picture is of West Rongbuk Glacier with Mount Everest in the background. The top picture was taken in 1921, and the bottom one was taken in 2009. You see that the increase in atmospheric warming, glacial melting has caused anomalies in natural systems, and snow and glacial melting threatens the life of about 2 million people that are living downstream of the Himalayas. The Indo-Gangetic plain is one of the largest black carbon source in the world because of the lifestyle that is heavily dependent on black carbon for agricultural, food, and transportation. And the thick haze over South Asia that you see in most satellite images has become more frequent nowadays. The large rate of emission from Indo-Gangetic plain responsible for that haze it alters the amount of radiation received by the region, which can be seen in the bottom left figure, which is the aerosol optical depth for 550 nanometer. The picture on the left is from one of our sites in the Kali Gandaki Valley that shows a haze layer that is almost a kilometer deep. There are several trans-Himalayan valleys, like the Arun Valley and Kali Gandaki Valley, that connect the Indo-Gangetic plain to the Himalayas. And the air mass that gets funneled through these valleys transport and deposit particulate on snow and ice. The air mass that penetrates this mountainous region through valley follow the dendritic pattern of the valleys. And the extrapolation of modest imagery in the Arun Valley shows that aerosol layer penetrates into the valleys, and the aerosol, the height of the aerosol is as high as the ridge lines. The Himalayan valleys have very well-developed wind system, and it is especially developed during the dry season when the aerosol haze is very common over the Indo-Gangetic plain. Like I mentioned earlier, Kali Gandaki Valley is one of the major connecting pathways, and it is about 130 kilometers long and is about 5,000 meter deep in places in the middle of the valley where mountains tower from the both sides. The winds are thermally driven, and that's the average velocity of wind you'll see is about 10 meters per second during daytime and 3 meters per second at night. This is the wind profile, which shows a diurnal wind pattern within the valley. The valley has a very distinctive daytime flow with gusting wind that average about 10 meters per second during the day and crossing the 15 minutes per second mark every day, which is very different from the nighttime flow, which are at an average of approximately 3 meters per second. And the wind direction plot here shows you a switch between the up valley and the down valley flow. The down valley flow, you can see that it is very different from what the up valley flows are in the valley. The reason for this distinct wind pattern is because the mouth of the valley is densely vegetated, but as you move up the valley, it becomes more arid, and this fuels the pressure gradient within the valley for strong thermal flows during the day, which when the gradient is very strong. And there are 2 stations in the valley that we'll be looking at the data from. So Lomanthang is situated in the southern edge of the Tibetan Plateau and is at the head of the river valley and has a very arid landscape. Here we only have an automated weather station. Our main station is in Dumsum, which lies in the middle of the valley and experiences the strongest wind gusts. And University of Virginia has maintained the lab since 2010 at an elevation of 3,000 meters, and we have weather station at 3,500 meters in Zomsom. The lab is equipped to measure carbon monoxide, black carbon, ozone, and meteorological parameters. This is the time series of black carbon that shows a diurnal pattern with higher concentration during the day and low at night. The increase in concentration of black carbon in the valley coincides with the onset of up-valley flows, and the concentration drops after the up-valley flow dissipates and continues to drop until the next day when the up-valley flow picks up again. Black carbon also exhibits a seasonal pattern where BC concentration in the valley is very high during pre-monsoon season compared to that of the monsoon season because the air pollutants don't get washed out as much. And between April and comparing the data of April 2012 13 versus August 2013, you see almost 89% higher black carbon concentration in the valley during spring. And to reinstate again that this is the time when you see a very thick layer of haze over the Indo-Gangetic plain. Other than the diurnal and the seasonal pattern, there are regional transport episodes when the regional transport events cover much of South Asia in haze for an extended period of time. Calypso imagery of 14th April shows a couple kilometer deep aerosol layer denoted by the orange color that is over the Indo-Gangetic plain leading up to the high Himalayas. And we distinguish the local pollution event from regional transport episodes of black carbon by using the carbon monoxide data. If you look inside that box, with the peak in black carbon, you also see a peak in carbon monoxide, which shows that it is a local pollution event, versus in that box where even though the black carbon concentration increases, carbon monoxide remains the same. And the reason for it is carbon monoxide is very fairly mixed by the time it comes up to the mountains through these valleys, if it is emitted far away. But if the emission is very close to the site or within the valley, you see the peak that goes over the background concentration of carbon monoxide. Similar to BC, ozone also shows diurnal variability, and ozone is produced downwind of the pollution source. There is a lag in ozone concentration as it is not detected as soon as the sunrise or there is enough sunlight for the photochemical production of ozone. But with the onset of up-valley flows, which indicates much of it is being transported up the valley rather than being formed within the valley. Ozone also exhibits a seasonal pattern with more ozone concentration during pre-monsoon season versus the monsoon season. But how much of it is due to pollution downstream of the Himalayas, as ozone precursors do not undergo wet deposition during spring, versus what is due to the stratospheric intrusion? We'll be looking more into it in spring of 2015, where we will be launching ozone sondes south of the Himalayas to look at the vertical structure of the ozone and figure out why there is the seasonal variability in the ozone concentration that we see in the valley. And in conclusion, we see that there is a higher black carbon concentration in the valley, which onsets with the strong up-valley wind, and BC is significantly higher in pre-monsoon season versus during the monsoon season, and regional transport episodes that last for a few days that does not correlate with higher CO concentration is due to local pollution events, and also that ozone shows diurnal and seasonal variability. With that, I'd like to acknowledge my funding sources, my advisor, and thank you for your attention.
Okay, we do have time for questions, please.
Yes.
The local events seem to be fairly significant. What kind of sources are in the valleys?
In the valleys, these are mainly rural valleys, so you see a lot of biomass burning, and it is usually a significant amount if they are like burning vegetation stuff. So that's what you see for the signature of local valley events. And sometimes there's also transportation. It is not a very regular transportation system there, so you see like the peaks. Sometimes if the wind is blowing towards the station, then you see those peaks as well.
Additional questions?
Yes.
So, do you use data rolling pattern for your ozone time series? And second question is, we see a distinct diagonal pattern for almost all the periods except for amphibian episode in the middle where we don't see any specific diagonal pattern.
I'm sorry, what was the first question?
Do you use an data rolling average for your ozone or
Ozone averages are 10 minutes average, and they are like connected continuously. And for the peak, that you don't see the peak at sometimes is because of whatever the background pollution is, and the atmosphere is pretty much cleaner. That's why you do not see spikes all the time, but only during certain times.